UVM TLM Transaction Level Modeling is a modeling style for building highly abstracted models of components and systems. In this scheme, data is represented as transactions, class objects that contain a random, protocol-specific information, which flow in and out of different components via special port called TLM interfaces. This brings about a higher level of abstraction, which is very much required in today's verification environment because of a large amount of signals associated with different protocols. It would be a lot it would be a lot simpler to understand, debug, and verify if we can represent the data and changes in signals as transactions, like a write operation and read operation. UVM provides a set of transaction-level communication interfaces that can be used to connection between components such that data packets can be transferred between them. The good part about this setup is that it isolates a component from the changes in other components and promotes reusability and flexibility because now you can just swap the component with another which also have a TLM interface. Simple packet class object will be a transaction that can be sent from component A to component B via TLM interface, port, and export. Okay. Next is TLM blocking put port. Any component can send a transaction to another component through a TLM put port. The receiving component should define an implementation of the put port. The implementation gives the receiver the chance to define what has to be done with the incoming packet. The port can be either blocking or non-blocking in nature, which will decide whether the put method will block execution in the sender until the receiver accepts the object. The example shown below is the TLM blocking put port in one component connected to its implementation port in another component. UVM TLM port example. A class called packet is defined below to act as the data item that will be transferred from one component to another. This class object will have two random variables that can be randomized before sending. 1. Create sender class with a port over type UVM blocking put port. A class called component A is created, which has a UVM blocking put port parameterized to accept a data object of type packet. The port has to be instantiated with a new method, prefer, preferably in the building phase of the same component. In this example, a class object of the type packet is created, randomized, and sent via the put port handled by calling the put method. Many such packets can be sent using a simple loop controlled by a configurable variable. 3. Create a receiver class that implement the put method. The receiver class needs to be defined on implementation port using UVM blocking put imp. Since the port is blocking in nature, the put implementation is a task which has to be defined by this component. 4. Connect port and inch implementation at a higher level. The connection between a port and its implementation has to be done at a higher hierarchy level, since both components are instantiated directly within the task class in this example. The connection between them can be done during the connect phase of the test. If these two components were instantiated in another component or environment, they have to be they have to be connected during the connect phase of that component or environment. Put port blocking behavior. The example shown above shows used a blocking put port declared of the type UVM blocking put port, which would store the sender from resuming until the put task returns. This blocking behavior can be observed if there is a delay inside the implementation of the put method within the component B. The code shown below insert 20 nano delay inside the put task. Note that the time is consumed by the component inside the put task, which blocks the sender from sending the next packet. At 20 nanoseconds, component B finishes the task and the component proceeds to send the next packet. And next is TLM non-blocking put port. UVM TLM non-blocking put port. A previous article showed example of using a UVM blocking port, TLM port that was blocking in nature, where the sender gets stored until the receiver finishes with the put task. Similarly, UVM TLM also has non-blocking method of type UVM non-blocking put, where the sender has to use the try put to see if the put was successful or can put method to see if the receiver is ready to accept a transfer. Like before, the UVM TLM non-blocking put port should ultimately be connected to a non-blocking put implementation port. UVM TLM non-blocking port example. A class called a packet is defined below to act as the data item that will be transferred from one component to another. This class object will have two random variables that can be randomized before sending. 1. Create a sender class with a port of the type UVM non-blocking put port. A class called component A is created, which has a UVM non-blocking put port. Parameterized to accept to data object of type packet. The port has to be instantiated with a new method preferably in the build phase of the same component. In this example, a class object of the type packet is created, randomizes, sent via the put port handled by the calling the try put method. Many such packages can be sent using a simple loop controlled by a configurable variable. The try_put function should ideally return 1 if the transfer is successful and 0 if it has failed, and should be provided by the receiver which implements the function. 3. Create a receiver class that implements the put method. The receiver class needs to be defined an implementation port using UVM non-blocking put imp. Since the port is a non-blocking is nature, so the the try put implementation as a function which has to be defined by this component. 4. Connect the port and each implementation at a higher level. The connection between A port and each implementation has to be done at a hierarchical level. Since both components are instantiated directly within the test class in this example, the connection between them can be done during the connect phase of the test. If these two components were instantiated in another component or environment, they have to be connected during the connect phase of that component or environment. Non-blocking behavior. The code snippet in the example shown above can be modified to model try-put in a blocking manner. Component A now uses a do-while loop for multiple attempts until try-put is successful. So implementation of the try-put function by component B is changed to return a random value to model the readiness of the receiver. Try-put will return 0 if the receiver is not ready to accept. UVM TLM can put example. Instead of directly trying to put a packet, the sender can first query to see if the receiver is ready or not with the can-put function that sends the packet. The can-put function in the component B is set to return a random value in this example to model readiness of the receiver. Okay, next is put, export, and imp. UVM TLM port to export to imp. UVM TLM port and export are also used to send transaction object across different levels of the test bench hierarchy. Ports shall be used to initiate and forward packet to the top layer of the hierarchy. Export shall be used to accept and forward packet from top layer to destination. Implementation ports shall be used to define method at the target. Shown below are a few examples that use port, export, and implementation for components at different hierarchy level. Port to export to imp. Subcomp is a subcomponent within component A that is trying to send transactions to another subcomponent called subcomp B in component B. To maintain flexibility and portability of the code, it is recommended to allow subcomp A to send data to component A, which should then forward them to the top layer of the hierarchy. Component B shall accept the transaction and forward it to the subcomp B. A class called package is defined below to act as the data item that will be transferred from component to another. This class object will have two random variables that can be randomized before sending. Subcomponent A, component A, component B, subcomponent B. Okay, port to imp. In this example, component A forwards the packet from a subcomponent A to the destination component B. The only difference is that component B is the target and hence should define the implementation port instead of an export. Port to imp. In this example, component A is the initiator and sends a packet from its port to the destination subcomp B, which is implemented to put method. Since component B is the container for the target, it should have an export to forward the packet received from the connected port at the top level. Port to export to imp. In this example, there is an additional layer between component B and the target subcomponent B called sub-conf v1. This layer has to simply forward the packet to the destination and hence shall have an export. Next is blocking get port. Any component UVM TLM blocking get port. Any component can request to receive a transaction from another component through a TLM get port. The sending component should define an implementation of the get port. The implementation gives the sender the chance to define what needs to be sent to the requester. This is just the opposite of a port seen in a previous article. The port can be either blocking or non-blocking in nature, which will decide whether the get method will get execution in the receiver until the sender sends the object. The example shown below is TLM blocking get port in one component connected to its implementation port in another component. 자, UVM TLM get port example. A class called UVM packet is defined below to act as a data item that will be transferred from component to another. This class object will have random variables that can be randomized before sending. That one, the create sender class with a port type UVM blocking get imp. A class called component A is created, which has a UVM blocking get imp parameterized to accept a data object of type packet. The port has to be instantiated with a new method, preferably in the build phase of the same component. In this example, a class of the type packet is created, randomized, and sent via the implementation of get method. Note that it has an output of the type packet. Many such packets can be sent using a simple loop controlled by configurable variable. 3. Create a receiver class that waits on the get method. The receiver class needs to define the get port using the UVM blocking get port to receive the packet. Since the port is blocking in nature, the get method implementation is a task that was defined by sender shown above. The connect to port and each implementation at a higher level. The connection between a port and each implementation has to be done at a higher class hierarchy level, since both components are instantiated directly within the test class in this example. The connection between them can be done during the connect phase of the test. If the two components were instantiated in another component or environment, they have to be connected during the connect phase of that component or environment. Get port blocking behavior. The example shown above used a blocking get port declared of the type UVM blocking get port, which would stop the receiver from resuming until the get task returns. The blocking behavior can be observed if there is a delay inside the implementation of the get method within component A or the sender. The code shown below insert a 20 nanosecond delay inside the get task. Note that time is consumed by component inside get task, which blocks the sender from sending the next packet. At 20 nanoseconds, component A finishes the task and proceeds to send the next packet. Next is non-blocking. Next is non-blocking get port. TLM non-blocking get port. A previous article shows an example of using a UVM blocking get port. TLM port that was blocking in nature, where the receiver gets stored until the sender finishes with the get tasks. Similarly, UVM TLM also has a non-blocking method of type UVM non-blocking get port, where the sender has to use the try get to see if the get was successful, or can get method to if the sender is ready to start a transfer. Like before, the UVM TLM non-blocking get method port should ultimately be connected to a non-blocking get implementation port. The UVM TLM non-blocking get example. A class called packet is defined below to act as a data item that will be transferred from one component to another. This class object will have two random variables that can be randomized before sending. One create a receiver class with a port of a type. A class called component B is created which has a UVM non-blocking get port, parameterized to accept a data object of the type packet. The port has to be instantiated with a new method, preferably in the build phase of the same component. In this example, a class object of the type packet is received via the get port handle by calling the try-get method. Many such packets can be received using a simple loop controlled by a configurable variable. Try to try get function should ideally return 1 if the transfer was successful and 0 if it is failed, and it should be provided by the sender which implement the function. 3. Create a sender class that implemented the get method. The sender class needs to define an implementation port using UVM non-blocking getImp. Since the port is blocking in nature, the try-get implementation is a function which has to be defined by this component. The connect port and its implementation at a higher level. The connection between a port and its implementation has to be done at a higher hierarchical level, since both components are instantiated directly within the task class in this example. The connection between them can then be done during the connect phase of the test. If these two components were instantiated in another component or environment, they have to be connected during the connect phase of that component or environment. UVM TLM can get example. Instead of directly trying to get a packet, the receiver can first query to see if the sender is ready or not with can get function and get the packet. The can-get function is component is set to return a random value in this example to model readiness of the receiver. Simulation log. Okay. Next is TLM 5.0. Okay, TLM 5.0, UVM TLM 5.0. Assume data rate of the sender is much faster than the rate at the receiver at which the receiver can get packets. A FIFO element is required in between to store packets so that it allows both the sender and the receiver to independently operate. Depth of the FIFO is typically calculated based on the rate of the data transfer. A TLM FIFO is placed in between test bench components that transfer data object at different rate. The UVM TLM FIFO example. A class called a packet is defined below to act as a data item that will be transferred from one component to another. This class object will have two random variables that can be randomized before sending. So one is create a sender class with a port of the type UVM blocking put port. A class called component A is created which has a UVM blocking put port parameterized to accept a data object of the type packet. The port has to be instantiated with a new method, preferably in the build phase of the same component. In this example, a class object of the type packet is created, randomized, and sent via the put port handles by calling the put method. Many such packets can be sent using a simple loop controlled by a configurable variable. To create a receiver that I receive using the get method, the receiver class tried to get an item using the UVM blocking get port. 3. Connected to the component via the TLM FIFO at a higher level. The connection between the two components via TLM FIFO has to be done at a higher hierarchy level. Since both components are instantiated directly with the test class in this example, the connection between them can be done during the connect phase of the test. If these two components were instantiated in another component or environment, they have to be connected during the connect phase of that component or environment. The UVM TLM FIFO in this example is defined to have a depth of 2. The put export is connected to the first component, put port, and the get port is connected to a receiver's get port. So you can see that we connected both ports in a component A to AB to the export in TLM FIFO. The next is UVM TLM example. This UVM TLM example. This UVM TLM example uses put port and TLM FIFO and get port discussed in the previous articles to build a test bench that has TLM port at a different level. TLM FIFO can be extended to have another component called component B, accept packets using another internal FIFO and subcomponent. A class called packet is defined below to act as the data item that will be transferred from one component to another. This class object will have random variables that can be randomized before sending. Subcomp1. This component is exactly the same as the UVM TLM FIFO example and start sending packets using UVM blocking purport. Subcomp2. This subcomponent is slightly slower than in receiving packets compared to one and seen and above, and accepts data through the UVM blocking get port. Note that that also has another put port of type UVM blocking put port of forward data out of the component A. Component A. This layer contains both subcomponents connected together by a TLM FIFO since their transfer rates are different. Note that it also has another put port of the type UVM blocking put port to forward the packet it received from the subcomp 2, which is at a lower layer. Subcomp 3. Assume that a destination component is even slower than the other component seen above the accepted packet using a UVM blocking get port. Component B. Another UVM TLM FIFO is required to be connected to a subcomp 3 to buffer packets received because of a slower rate of the destination. Note that this has a top-level put export port of the type UVM blocking put export. The top env underscore test. The connection between a port and its implementation has to be done at a higher hierarchy level, since both components are instantiated directly with the test class in this example. The connection between them can be done during the connect phase of the test. If these two components were instantiated in another component or environment, they have to be connected during connect phase of that component or environment. Simulation log. Next is analysis port. Next is TLM analysis port. The put and get communication we have seen earlier typically requiring a corresponding export to supply the implementation. The idea behind having an analysis port is that a component like monitor should be able to generate a stream of transactions regardless of whether there is a target actually connected to it. The UVM analysis port is a specialized TLM-based class whose interface consists of a single function, write, and can be embedded with the component as shown in the snippet below. This port contains a list of analysis exports that are connected to it. When the component monitor calls analysis port write, it basically cycles through the list and calls the write method of each connected export. If nothing is connected to it, then it simply does not do anything. The advantage lies in the fact that analysis port may be connected to zero, one, or many analysis exports and allows a component to call write method without depending on the number of connected exports. Also, it's worth to note that write is a void function and hence will always complete within the same simulation data cycles. Example: let's take a component B from the TL input example and connect three subscribers to it. In order for a component B to broadcast a transaction to each subscriber, there needs to be a special channel for communication. This is implemented by analysis port. Analysis port can declared using the UVM analysis port so that the component B can send the transaction into channel. We will see how we can connect a subscriber to this channel in a short while. Declare the analysis port. Define analysis port implementation. Now let us create a subscriber component parameterized to simple packet data type. Note that the subscriber implemented the right method for our purpose. We can just display a message because we have derived our subscriber from UVM subscriber. It already has an analysis port implement object predefined by the name analysis export, hence we won't have to clear another implementation port of our scope, our purpose. See the snippet of the UVM subscriber class below. Note that the analysis port given by UVM analysis port are always connected to each implement port declared using UVM analysis imp. Function write as a place where you need to implement the operation are required to be done on the incoming transaction. In this example, we are simply printing an acknowledgement statement. Like here, component analysis port with its implementation. Since all our components are instantiated within the environment myenv, it is easier to connect between the components at this level. This is done by the connect phase method, where the analysis port of the component B is connected with multiple implementation ports defined within each subscriber. Get the source code or this example from our download page titled TLM AP access analysis port. Okay, next is a sockets. The TLM sockets. The TLM 2.0 introduces a socket which enables asynchronous bidirectional data transfer between the initiator and target component. A socket is derived from the same base class as port and export UVM port base. Components that initiate transactions have initiator socket are also and are called initiators, which while the components have received the transaction have a target socket and a called target. Note that the initiator socket can be connected only to target socket and target sockets only to initiator socket. The test bench. Let's take a look at the initiator component to see a socket is declared and used. The time annotation argument used in a B-transport method allow the timing point to be offset from simulation times at which task is called and returned. Consider the target socket and you will see You will see that is very similar to the port and export scheme we saw in previous session. The missing link is connection between two sockets, and the best place to do that is the environment where both initiator and target components are instantiated. Next is using UVM TLM underscore declare the macro in TLM. Using underscore DECL declaration DECL macro in TLM. We will see in the scenario TLM put where the data sent to be a component B is executed using the put method defined in B. Let us consider the case where there are two components A and B connected to B's export. Then any data object sent by either component A or component C will be received by component B and operated upon the same put method. If there is a need to be able to process them separately, you would need them to separate put method. The UVM provided us with a UVM start put implement declare macro to deal with the cases when the component needs to avoid two put implementation port. Now the following from the sample code above, they should be outside the class. UVM put input declared should be outside the class. UVM put input class used inside my put input should have the argument passed to the macro appended to it. Put function task should also have the argument appended to it. UVM will create two new classes by the name UVM put input underscore 1 and 2 when the macros are called. That is the reason why you have to append the argument, the UVM put input, when the trying to create an object. Even though two methods defined in those classes have the argument appended to it, you may give any name as the argument instead of underscore 1 and underscore 2, but make sure to use the same afterwards. Example, let's first create a component A and component C. As coming to the component B, notice that we have used the same code shown before implemented the macros. Environment will have all three component initiators and connect component A and component B, put put underscore input one port, while the component C will be connected to a component B put input 2. Okay, thanks. I think this over the UVM TLM about the UVM TLM. Thank you very much.